Okay, we're going to talk about half-life today. So what that is, it's the half-life of an element is the time it takes for half of the material you started with to decay into a different isotope. So after one half-life, there's going to be half of the original sample you had left. So if you started with 100 grams of some sort of isotope, after one half-life, well, you're going to have half of it, so only 50 grams will be left. After two half-lives, there'll be half of the half, or a quarter of your original sample left. So again, if you started with 100 grams, goes through one half-life, you'll have 50 grams. After the next half-life, you would have 25 grams. So every time you go through a half-life, you divide your sample by 2. So each element has its own half-life. So for example, so each element will decay into a new element, and the half-life of each element is constant. It's kind of a fingerprint for each isotope. So let's say again, like you have 100 grams of radioactive carbon-14, which that carbon-14, that's the carbon we use for carbon dating, for radioactive dating, to see how old things that used to be living, how long ago did they die. So the half-life of carbon-14 is 5,730 years. That doesn't change. It always stays the same for carbon-14. So you can use that to figure out how old something is based on how much carbon-14 is left in that specimen. So this means that after 5,730 years, well, if you start out with 100 grams, you would have only 50 grams of your carbon-14 remaining. After 11,460 years total, which would be 2 half-lives, you'd only have 25 grams of that carbon remaining. After 17,190 years, you'd have half of that, so 12.5 grams that will remain, and so forth. So this is the pattern that we would see for these types of calculations. Okay, so there's a couple ways to calculate, or how you can kind of set up a half-life problem. There's the chart method, which we'll try that for a problem that we have, where you take note of the mass you're starting with, the time that's passed, and the number of half-lives that have occurred. So you'd always start out with, well, the mass depends on the problem that you're working with, so we'll see that in a bit. You always start with the elapsed time, or time 0, because no time has passed, and then a half-life 0. And you would have half-life 1, half-life 2. The elapsed time and the mass will depend on the problem you're working with. The mass will be divided by 2 every time you go down. Okay, so let's try out. We're going to do that, and also kind of another way, if you're not a big fan of doing the chart method, there's another way you can do it that's just the same way, it's just not organized into a chart. So you can decide which way you like to do it. Okay, so sample problems is, first types of problems which are easier is where they give you the number of half-lives that have occurred. Okay, so let's do number 1 with the chart method, and we'll try number 2 without an organized chart per se. So a sample of 0.25 grams of some radium isotope undergoes 3 half-lives. How much of the sample remains? So how much meaning the mass. So mass, question mark. Okay, so we can set up a chart here. Where we're taking note of the mass we're working with. We're taking note of the time that has passed based on if there was kind of a half-life time given to us, which in this case, we won't really need that. So we can kind of ignore this middle column here. And we need to know the half-life. Okay, so this problem didn't give us years or anything like that, so we're not going to have to worry about the time for this one. We started with 0.25 grams. Okay, this would be at half-life 0. Okay, so it wants to know how much is going to remain after 3 half-lives. So after 1 half-life, the mass is going to get divided by 2. So that would be, you would have 0.125 left. Okay, so after 1 half-life, you would have 1.125 grams of your sample. After a second half-life, again, half-life means you're dividing by 2 your sample. So your previous mass, 0.125 divided by 2 would be 0.125. 0.0625 grams. And then your third half-life, you would have that previous sample, 0.0625 divided by 2. So you have 0.03125 grams left. Now let's just say just to kind of do a time thing here, let's say every half-life happened every, let's say 27 years. Let's just throw that in there. So if we threw in that this had a half-life of 27 years, well, this initial half-life, the time passed would be 0. After one half-life, 27 years would have passed. After a second half-life, it'd be 27 years times 2, which would be 54 years. And if, again, we're working the sample problem to see after 3 half-lives, well, that'd be 27 years times 3, which would be a total of 81 years. So just wanted to throw that little extra thing since this problem didn't have that in there for you. Okay. Oops. Okay, there we go. All right, now let's do one, or maybe you're not like a big fan of setting up a chart like that. You can do the same thing, just kind of a little, just more kind of free-flowing here. So a sample of sodium has a starting mass of 18 grams. How much sodium will remain after 4 half-lives? Okay, so we know that every time it goes through half-life, you divide by 2. So 4 half-lives, what that means is that you're going to divide by 2 4 times. So if you have 18 grams, we know we're going to divide that by 2 4 times. So your answer is going to have, well, grams. So you remember, put a unit for your answers all the time. So 18 divided by 2, divided by 2, divided by 2, divided by 2, or 18 divided by 2 to the 4th power. You can do it that way too. And you would have 1.125 grams left behind. That'd be your answer. And then if they wanted you to know, like, let's say again, if we were working with a time and it said this happened every 15 years, well, we went through 4 half-lives. So that would be after 1 half-life, 15 years, 2, 3. So after 1 half-life would be 15 years, another half-life, that would be another 15, and another half-life there, 15. So that would be a total of 45 years. Okay. Wait, oops. Gotta add that one. Whoops, sorry about that. Scratch that, it'd be 60 years. Sorry about that. So that's another way you can kind of set up a problem without doing a chart per se. Okay, so these are problems where if they gave you the half-life time, or the number of half-lives that occurred. Sometimes you don't know how many half-lives that have occurred, so you would have to figure that out first, okay? Okay, so we'll do this one as a chart method, and one without the chart method. So mass, time, and half-life. Okay, so here, 20 grams of an isotope has a half-life of 25 years. How much of a sample will remain after 100 years have passed? Okay, so this one, we know we're starting out with 20 grams. No time has passed. Okay, and we want to know, how much is going to remain after 100 years. And we know every 25 years is a half-life. So for time, after 25 years has passed, we'll say all these are years, that would be 1 half-life. And the mass is going to be divided by 2 every time we go down this column. So 20 divided by 2 would be 10. Okay. Another half-life would be another 25 years, so that'd be a total of 50 years. And that would be half-life number 2. Divide the 10 grams by 2, you'd have 5 grams left behind. So we're going to do this until we get to 100 years. Another 25 years has passed to get a half-life, so 75 years, that's the third half-life. So we have 2.5 grams remaining. And then finally, we're going to reach our 100 years. So the problem says what's going to remain after 100 years? This would be the fourth half-life, so it went through 4 half-lives. How much of the sample will remain? Well, 2.5 divided by 2 would be 1.25 grams. So that would be your answer. Okay. So if you don't like doing the chart method, like this next one, you can do sort of the same. You can do the same thing without setting up a chart. So an isotope has a half-life of 1600 years. You start out with 100 grams. How much of the sample will remain after 4800 years? Okay. So how to do this without the chart? This is the total time that passed, and this is the time, so 4800 years for the total time that has passed. Every 1600 years, there's a half-life that's occurred. So between these two numbers, the time numbers, you can figure out how many half-lives occurred by dividing them. So if you're not a fan of the chart method, if you're given two different time increments, you're going to do the total time, or the bigger number time on top, 4800 years, divided by, let's make this a nicer 0, divided by the time it takes for one half-life to occur. This will tell you how many total half-lives have happened. Okay, so if you do 4800 divided by 1600, you would get, 3 half-lives. That tells you the number of times to divide by 2 for your mass. Okay, so we start out with 120 grams, and we're going through 3 half-lives, meaning we're going to divide 120 by 2 3 times. So 2, there's our 3 half-lives, okay? So 120 divided by 2, divided by 2, divided by 2, and you get a total mass of 15 grams as your answer, okay? So that would be your answer. So again, I wanted to show you both ways. If you like setting up a chart, awesome. If you don't like setting up a chart, you can do it this way as well, okay? So either way you want to do it, it's fine as long as you show all your work. And again, label your answer with the unit that you need. A lot of these cases it's grams because you're finding a mass. Okay. All right, thank you.